Alright, so let's take a look at the post-lab questions. The first three questions are referring to the lab experiment that you did. Question number 1 says, if you used a larger mass sample, would the final temperature of the water be higher, lower, or remain the same? I know it's kind of confusing, but the larger mass sample that we're referring to is the mass of the chunk of lead. So you had your calorimeter, and you had your amount of water. This is for question number 1, by the way. And in there you had your lead sample. And so you know that this lead sample, which is hot, right, has a certain amount of heat that's going to leave the water. But the idea is, what if we're looking at a scenario where we have a much larger piece of metal? Well, remember that piece of metal is at the same temperature. So a small piece of metal and a large piece of metal, if they're both at the same temperature, the larger piece of metal is going to be able to release a lot more heat. And if it's releasing a lot more heat, then we know that the temperature change of this scenario is going to be much greater than this scenario. So the correct answer is should be higher. All right. Question number 2, let me clear this real quick. So for question number 2, if a larger mass of water was used in the calorimeter, would the final temperature of the metal be higher, lower, or remain the same? So it's it almost looks tricky here. So it's saying the final temperature of the metal. Well, that's the same as the final temperature of the water. Right? We know that once they reach thermal equilibrium, they're both the same temperature. So you have two scenarios. What if in your calorimeter you used some amount of water, so you threw your chunk of metal in and you had a certain temperature change, right? So some value. And well, what if you did the experiment again, but this time you had used a lot more water? You still used the same piece of metal. The question is, how would your temperature change be affected? Well, remember, your water has a very large heat capacity. So, if you used a greater mass of water, then it's going to do a better job at distributing that heat across the entire mass. Whereas in the other case, there was less mass of water to distribute, therefore its temperature change would have been, it's easier to increase the temperature of a smaller sample of water. But if you have a larger sample of water, then if you're releasing the same amount of heat in both cases, then the larger amount of water, that temperature difference is going to be less than the initial scenario. So the final temperature of the water is going to be lower, which means the final temperature of the metal will also be lower. All right, let's take a look at question number 3. If a different liquid with a lower specific heat capacity were used, would the final temperature of the metal, or would the final temperature of the other substance or other liquid, be higher, lower, or remain the same? So in this case, you have your calorimeter, it had water in it, you threw your metal in there, right? Heat was lost, its temperature went up. So the question is, what if it was a different substance, a different liquid? Well, if it has a lower specific heat capacity, that means that it takes less energy to increase its temperature. Therefore, that means we're going to have a much greater, not much greater, but we're going to have a greater difference in temperature. It's going to rise much quicker. Much more quickly? Now, if you want an explanation in terms of the actual mathematical equation, we can do that. So let's take a look at the equation for a specific heat capacity. Specific heat capacity is equal to the amount of heat absorbed divided by its mass of that substance times its change in temperature. So we know that for water it was 4.184, right? Well, if it was another substance, which would be less than 4.184, so for example, let's just say we said 2.0, right? Well, the amount of heat that's going to be absorbed is going to be the same in both cases because it's the same piece of metal, whether it's going into the water or another substance. Well, the mass of the, assuming we have the same mass, it's the idea, right? Well, the mass isn't changing. So the question is, how is delta T going to change? Well, if on this side we went down from 4.184 to a lower number, for example 2, on this side, if this is constant and this is constant, how do you get a lower value? Well, you have to divide by a larger number, and the only thing that can change on the denominator is a change in temperature. So a greater change in temperature will result from using a substance with a lower specific heat capacity. Therefore, the final temperature of the metal should be higher. Alright, now let's take a look at question number 4. A sample of water is needed to drop the temperature of a metal. We have the specific heat capacity of the metal. From, we have an initial temperature. To, we have a final temperature. What is the mass needed? This is referring to the mass of the water. The mass of the metal is given to us. The initial temperature, well, we know that the initial temperature of the metal and the final temperature of the metal is 110.5 and 45.5, so this initial temperature must be referring to water. So we're trying to find the mass of the water. So let's get started. Let's see what we know and what we don't know. So we know, or we should know, that the heat that the metal is losing is equal to the heat that the water is gaining. Remember, it doesn't matter what side the negative is on. I could have just as easily put the negative on this side. It doesn't matter. So, if we know that the heat that the metal loses is equal to the heat that the water gains, and it's represented by Q, we also know that Q is equal to MC delta T, right? MCAT, right? So, that means that the MCAT of the metal is equal to the negative MCAT of the water. So if we did MC delta T of your metal, that's equal to negative, right? And we have the MC delta T, that was a horrible delta, delta T of your water. Now, let's check. Do we know the mass of the metal? Yes. Specific heat capacity of the metal, given to us. Change in temperature? Yes, we know the final, we know the initial. Do we know the mass of the water? No, that's what we're trying to find. Do we know the specific heat capacity of water? Yes, we do. Do we know the change in temperature of water? Well, we're told the initial temperature, but do we know the final? Well, even though we're not told what it is, we're told what it is. Remember, the metal is going to be cooling down, the water is going to be heating up until they reach the final temperature, or an equilibrium temperature. If we know that metal's final temperature is 45.5 degrees Celsius, well, that must also be the water's final temperature. So, yeah, we do know the change in temperature of water. So, clean up the setup a little bit. We know that the product of this is equal to the negative product of this, and we need to solve for the mass. Alright, so take all these numbers and multiply them. Take these two numbers and multiply them, and we need to solve for the mass of the water. So if we took MCS delta T, and actually let me do it in the colors so that you can follow along. The mass times the specific heat capacity times the change in temperature of the water, and we set that equal to the negative mass of the metal times, mass of the water times the specific heat capacity of the water times the change in temperature of the water. If we rearrange, we will get the mass of the water is equal to, and we throw everything else to the other side, we've got the mass of the metal times its specific heat capacity times its change in temperature divided by, and we threw the other stuff over, negative the specific heat capacity of the water times the change in temperature of the water. And you don't have to worry about that negative, because this negative temperature divided by this negative temperature, yes, that will give you a negative, but then times this negative will make it go away. So you'll end up getting a positive answer, and whatever you get, that's your answer. I won't reveal what it is, but because I don't have a calculator on me and I don't feel like doing the calculations. Now let's take a look at question number 5. So we have an 85.0 gram sample of aluminum. We have an initial temperature, we have the specific heat capacity, we have a mass of the water. After enough time, aluminum and water have reached equilibrium of, we know the final temperature of both of them. We don't know the initial temperature of the water. Okay, perfect. Again, this is one of those scenarios where the heat that is exchanged between the metal and the water is going to be the same. The only difference is one of them is positive, one of them is negative, because the energy is going from one to another. Now in this case it says that the aluminum metal is initially 10 degrees Celsius and then the final temperature is 52 degrees Celsius. So what that tells us is that the water is actually warmer than the aluminum. So the water is actually heating up the aluminum sample. So here's the information laid out for us. We know the mass, the specific heat capacity, and the change in temperature for the aluminum. We know the mass of the water. You always know the specific heat capacity of the water. But now let's take a look at the change in temperature. So we know that the change in temperature is equal to the final temperature minus the initial temperature. And we know the final temperature. We don't know the initial. So you gotta do some math work. So here's our equation that we're going to use. Problem is, what we're trying to solve for is actually embedded in that delta T. So instead of writing delta T, we'll just go ahead and write parentheses final temperature minus initial temperature. So this is going to be fun for you math people. So basically we just want to isolate initial temperature, and it turns out that it's not going to be that hard. So let's get rid of these guys first. So you've got mcs delta T of the metal. We're just going to go ahead and divide both sides by the mass of the water times the specific heat capacity of the water, and that's going to leave us with is equal to the final temperature minus the initial temperature, which is fine because now we just have to get rid of the final temperature. So very simple. Throw that final temperature to the other side. So it's like saying minus the final temperature is equal to. But if we compute this, this is going to come out to a negative value. Well, that's going to be equal to negative initial temperature. So it's pretty straightforward. Just flip the sign. Or if that is a struggle for you, you can just multiply everything by -1. And if you multiply everything by -1, that will change this sign to positive. That will make this negative and this positive. So, and then that's whatever you get as your answer. Hopefully it's right. So, that's it.